So within Chevron Lubricants, we've been looking at varnish and know that it exists in the systems for 20 plus years. But it's been over the last 7 years that we've really been starting to focus on, how much does this form? How can we address this? We're looking at it from a formulation standpoint in our finished products, but also, is there ways to do it to where we can actually come back into it and have our own system cleaner? There's been lots of cleaners out there on the market, but there's an unknown element to it. And so Chevron took it and said, we have to do some research here. So through our initial work of introducing Vartech ISC into turbine oil or power generation systems, we knew that there was something going on, that the varnish was plating out and creating temperature rises. Not only in just the areas or like in a bearing, but also in the overall system. And so the temperature was rising and not being able to regulate. So as we continue to explore this, we know that varnish has insulating type properties. And so anytime that film is created, it actually prevents the lubricant from doing its job, right? So the lubricant is meant to circulate through the system, removing heat, removing degraded materials or dust, particles, all of this stuff away from the operating surfaces. So as we moved into hydraulics, we actually had already a working performance stand, but we needed to take it down up one more level. And so one of those things to think about, when I brought up the idea of flow and temperature and chemistry and duration, these things have an impact. And flow is one of those things that if it's in a low flow zone, it's possible that the varnish starts to actually come out of solution more. Or if it's already an insoluble material, it can start to settle onto the surfaces. The other thing is temperature gradients. So when it is hot, solubility is increased. But if all of a sudden you have an area that is a little bit cooler in temperature, that varnish can then start to actually plate out a lot more. And one of those areas that we know is in almost every system is a heat exchanger. And so when we went into our hydraulic study, we actually wanted to look at and see if there was a direct impact into a heat exchanger. We had seen some of this within, as I said, the power gen and a smaller power turbine, to where the units were having to be shipped off-site to be rebuilt. So therefore we were thinking about that. How do we do that? And we actually then incorporated a heat exchanger plate model into our hydraulic system, to where this is a fresh plate and we can actually weigh this, we can build these up, changing the number of plates within the heat exchanger to see if that has an impact. There's also the ability of the flow rate that comes over all of the different formations of the plates. And what we actually did find is that we do actually are able to screen not only just different products and formulations of hydraulic fluids and the impact of how long does it take for them to start to degrade and start to form varnish. We can look at that. As we talk about the Vartech ISC, we now have a platform that is duplicating systems that are already in operation. This is a fully operating hydraulic fluid with a pump. It increases the pressure. We can change the flow rates over these. We can change the temperatures. We can do all those things that I was talking about, but now it's in a live enclosed system. And we can look at how the varnish is forming, how long does it take to form, when is there breaking points within the fluid, but then we can also come in and test Vartech ISC to how can we remove it. So within Chevron, this is what we like to do here at the Technology Center. We love to ask questions to ourselves and solve problems that are directly related to what the industry is needing. And not only just being able to answer them, but dive deep enough into it so that we have an understanding to be able to change something for the future.